Hello, everybody. Welcome to the second talk of our RSTalk series. The topic today will be Thermo-Hydro-Mechanical Analysis of Soil and Rocks. About myself, I am Kien Dang, Finite Element Group Manager at Rocscience. I am also the architect of IS2, IS3, and IS5 Finite Element Engine. Here are the agenda for today's talk. At the beginning, there will be an introduction of Rocscience, IS2 programs, and the newly added thermal module, followed by governing equations and formulations. At the end, some of the examples of typical applications such as artificial ground freezing, nuclear waste storage, seasonal slope stability, and Thermosiphon design for shallow foundations will be presented. As you know, Rocscience is a world leader in developing innovative 2D and 3D software for geotechnical engineering in mining, civil applications. For 25 years, we have built geotechnical tools used by over 10,000 users around the world. We are dedicated to delivering industry-leading software programs, exceptional customer service, and unparalleled technical expertise that engineers can rely on. We started development of IS2 programs, which at the time was called PHASE in the 90s, at a research group at the University of Toronto. And then in 1996, Rocscience was founded to provide various solutions for mining and civil engineering applications for the industry. Then in 1999, the name would change to Phase 2. It would change because we started to develop a 3D version of programs, which you all know is IS3. But at the time, it was called Phase 3. In 2014, the name would change to IS2 in 2014. And up to this version, we included seepage analysis, beard consolidations, dynamic community, and many advanced construct models for soil and rock. M+ were introduced in 2020 to provide more satisfactory customer support, and new features should be included more often. We had nonsense Barcelona-based soil models for unsaturated soil, vacuum consolidations, relief well, improved performance of dynamic analysis, including liquefaction analysis. And in last month, August 2022, we released thermal module, which will enable IS2 to run thermo-hydro-mechanical coupling analysis. Generally speaking, IS2 allows for analysis most of the geotechnical engineering design in soil and rock. Whether your project is civil or mining based, above ground or below, IS2 enables you to effectively analyze stress deformations, stability, support designs, and stage excavation with ease. You can also factor in groundwater flow with IS2 integrated seepage analysis tools for steady state and transient conditions for dams, embankments, slopes, tunnel, and excavation. And of course, you also gain the ability to automate the slope stability analysis with shear strength reductions, which perform a finite element analysis to identify the critical strain reduction factor. It integrates seamlessly with Slide 2 programs, which were proven the most slope stability popular program in the market. IS2 also support consolidation settlements analysis for embankment, excavation, and foundation designs. We also provide a lot of tools to use for dynamic analysis, such as natural frequency analysis, motion data processing, and liquefactions. And recently, with the additional of thermal module, it enables IS2 to analyze and evaluate the effects of temperature changes to geostructure. By introducing thermal module, now we can do fully couple of thermal, hydro, and mechanical in IS2. temperatures, we have the effect on solids by thermal expansions and thermo-induced strength effects. And water, we have effect on the temperatures by fog convections, whereas the temperature will affect the waters by the polarized behavior, natural convections, or thermo-induced hydraulic properties. And of course, with the solid and water couple using the beard couple approach, the interaction between water and solid will also be accounted for. Just a note here that we don't actually account for the effect of solid on the temperatures directly. We can, however, account for that effect indirectly to the effect of solid on the water and from the water to the temperature, as you can see from the chart here. Thermal module can be activated in the project setting, and you can turn on and off on the design behavior, such as natural convections, fog convections, or polarized-induced seepage, as you can see here. And here is a very simple example to show the interaction between the fluid and thermal phases. Three models were created to model the effects of frozen pipe on the surrounding environment, and the water flow from the right to the left for the two models that we have the fluid effect on. The first one only consider the thermal conduction only. The second one, when we have the effect of the fluid on thermal, one way. And the first one, when we actually activate both way couple between the fluid and thermal. And as you can see here on the first model, the temperatures around the freezing pipe is symmetric. However, because of the water flow here, we can see that there is a minimal effect of the frozen pipe zone on the upstream of the models. And when you account for the effect of the temperatures on the fluid, we can see that there is an extension of the frozen zone vertically on the model. And here is the water flow in the model after the simulations. And on the third model, when we activate the both-way couple, we can see that surrounding the frozen pipe, there's no water movement because basically all of the waters around the frozen pipe was frozen and no water can flow. And here is the math behind the scene, and I know that most of you will not be interested in this, so I just go very briefly about this. But here is the equation that we put everything together to solve to get the effect of temperatures, fluid, and deformation altogether. And the convection term here accounted for the heat transfers by water flow is included in the KT here, which is the conductivities matrix for the thermal term. And moreover, with the water content changing, the thermal property can also be changed depending on the thermal model that we use. Also, the permeability matrix H and the compressibility matrix also include the function of temperature, of permeability, and water contents. We also provide many boundary condition types that can be used for most of the applications involve thermals. Users can assign temperatures or display boundary conditions at a constant of temperatures. It can apply to node or segment, or it can be uniform along the surface shear, or it can be very linearly along the surface. You can also assign n factor to offset the temperature that actually applied on the surface. A second type that we provide is the heat flux or Norman type that can be assigned to node or segment as well. It can also be constant or time dependent. We also provide climate functions where or it can be called a surface energy balance. where the effect of solar radiation, vegetation, snow cover, wind speed, and air temperature can be accounted for altogether. Note that when you don't apply the flush body condition on the surface and there's no temperatures body condition, it is a special case called the perfectly insulated surface, which means that there will be no heat in and out from the surface. We also include the convection body condition where we can account for the heat transfer between the two medium. For example, you want to account for the heat transfer between the air and the solid, or you want to account for the heat transfer between the fluid and the solid phase as well. We also provide the insulations or a thermal contact. As you can see here in the figure, there's thermal contact between the two materials here. And you can either specify it as a perfect insulation, or you can specify it as conductivity for the thermal contact, or you can select none, which means that the temperature drop here, as you see here, that temperature drop, it could be equal to 0 when you select none here. And for the perfect insulation, the temperature between the two materials are not related at all. Or you can control the temperature drop here by specifying a conductivity or thermal conductance. Another very condition we provide is thermosiphon, and thermosiphons was widely used since 1960 in the Arctic climate where soil freezing is accomplished passively. For example, you don't need to use any power to run the system. And they can be assigned automatically in IHU. User can have three options to do that. You can either assign manually or use already established methods such as the Arctic Foundation or Zailing Enhanced method. We also provide many methods to model the behavior of the soil in thermal analysis. And for example, for the conductivities, you can have constant, you can have Johansson's or Johansson and Lou, you can have Davy, Cote and Pratt, and of course you can have the custom type, which means that you can input the conductivity manually, dependent on the temperatures or water content. And here is the typical thermal conductivity changing with the variation of degree of saturation, as you can see here in the graph. And another very important properties for thermal analysis is the heat capacities. We have three ways to model heat capacity in IHU. You can have constant heat capacity, you can have Jan-Newman's method, and of course you can do it at custom. Using the Jan-Newman methods, the effects of ice, water, and solid contribution to the heat capacity will be automatically accounted for. You can also specify to include the latent heat or not. So as you can see here in the figure on the right-hand side, as the temperatures approaching the freezing point, which is close to 0 here, the heating capacity of the material increase exponentially. Because that in that model we accounted for the latent heat, right? And this is causing a lot of issue in conversion when we accounted for the phase change in thermal analysis. Traditionally, this behavior requires very long time step to capture the front phase correctly. However, in IHU, and we developed an entropy compensation scheme that it will always capture the energy correctly from the phase change behavior, and so you can use much larger sum step without worrying much about the accuracy of the results. It also results in the excellent conversion rate as well. And one of the most important characteristics when modeling thermal in soil or rock is the unfrozen water content curve, and it's extremely important to calculate the effective conductivity, effective heat capacity, and it's also very important to capture the phase change phenomena in geomaterials. And here is the typical unfrozen water content curve for soils, and you can see here at the soil temperature is less than 1.5, minus 1.5. The unfrozen water content is 0, whereas it keep increasing at the temperature increase, and when the temperatures above the frozen point, and the unfrozen water content will be equal to the water content of the saturated value. And we provide several methods to do that. You can use methods from Conrad or Ty and Anderson's. You can even use the water content curve from the hydraulic properties such as Van Nostrand, or you can use a curve from Fetland and Singh, you name it. And so the question here is that many of you may not have enough data to have one of this fancy model available, and you only need to, you're only interested in a very simple simulation to see how it behaves. So we also provide a simple model here, which is only require one single parameter, which is the frozen temperatures. And you can also input it manually using the tabular form as well. And we also have the capability to account for the thermal, the specificity, and thermal expansion, of course. After finished computing, user can easily see how much heat was transferred to the sections using the heat transfer sections, and all of the thermal properties such as conductivity, heat capacity, unfrozen water content, and thermal results such as temperatures, heat flux, heat gradient, heat flow length can also be visualized by contouring as well as the history query, as you can see here. For the history query, you can also visualize during the calculation as well to our engine UI, where you can see the temperatures, the placement, and pressure changing during the calculation. So the first application example I'm showing today is the artificial graph freezing, or AGF. Graph freezing perhaps is one of the most popular graph support methods in mining and civil and environment project even. It is sometimes the most preferred methods because because of its low impact to the environment. And in this typical example, I actually will use to back analyze an artificial graph freezing design for a turnback tunnel of Guangzhou Metro Line 3, based on the paper of Jan et al. In 2019. The tunnel has the height of 9 meters and the width of 11 meters. It's located in the sandy clay layers at 12 meters below the ground surface, that you can see here. And the groundwater level is at 1.76 meters below the surface. The requirement of the design is that the effective thickness of the frozen zone had to be 2.5 meters. And in order to achieve that, they have been installed the series of the pipe outside of the tunnel battery. Here, the tunnel battery, you can see here, and here is the series of the pipe here. And the brine was pumped through the closed system from our freezing stations, and the temperatures of the inlet and outlets will measure, and the brine temperatures will control to achieve and maintain that frozen depth until the design support will install. And here is the brine temperatures from the paper. And here's the model in IHU. So here we only pay attention to the thermal design. So we did not want to be overcomplicated the model. And we just, so we didn't account for the groundwater level. But instead of doing the full seepage analysis here, we just need to set the water content value to 0.278, which is equivalent to the porosity of the material. The convection boundary condition will assign on the top to represent the interaction between the air temperature and the soil. And the dry or the frozen pipe was modeled using the convection boundary condition as well as in the convection number 2 here. And the medium temperatures were assigned with the bright temperature as shown in the previous slide. And here are the frozen zone calculated from the IHU, and the results will compare with the results from the paper. And you can see that the zones are very similar at the day 30 with the thickness of 0.7 meter. A very similar behavior were observed at the day 80 as well, when we have the thickness of 2 meter in the both IHU and the paper. And the thickness of 3 meter were achieved at the day of 130, and the same behavior was seen in IHU and the paper as well. Another example I'm presenting today is to evaluate the stability of geological repository of used nuclear fuel. In this example, we back calculated the design from Cavagno and Zikovic for nuclear waste management organizations for long-term management of Canada's used nuclear fuel. The layout of the repositories was shown on the right side, like as you can see here. Also, the fuel cells are stored at 2 levels, approximately 2.3 million bundles per level, with the lower level start 20 years after the start of the first level. Here is the longitudinal sections with buffer boxes. The center to center distance between the boxes at 1.5 meters, and between the boxes at 0.5 meter of the filled with bentonite pellets. And you can see that the top and the bottom rows are offset. And here is the model in RSTalk. We are doing the analysis for the case that have 25 meters room spacings. The repository levels are located between 400 meters and 800 meters below ground surface. In this particular example, because the area of interest are far away from the ground level, so we don't have to include the effects of climate to save the computational time. So the temperature of 5 will apply to the top, and 35 degrees was applied to the bottom. The initial temperatures will vary linearly along the model. The heat flux for each box were calculated from Mark II used fuel cell generations as shown in this table. And you can see that the heat flux degree by time. And also please note that the used cells only placed after 30 years of the uses, so the value of the heat flux occur at the 30 years will be used for the installation stage. And those value was all calculated from the Mark II used fuel heat generation source term. The drop was modeled using the hook brown materials, and the thermal property was shown in this table. And as you can see here, the thermal expansion's coefficient was 1e minus 5. There are two conditions for the design to be acceptable. The first one is the temperatures must not exceed 100 degrees over the whole time. And the second one is the repositories have to be stable. And here is the temperatures development at the side edge and the center point. The side edge is the line red and orange here, and the center points have the brown and the gray one like here. And as you can see, the result match pretty well with one from the paper. The temperatures at the center points rise immediately when the fuel cells were placed. It took almost 3 months for the edge points start raising the temperatures. And after 100 years, the temperature at the put point are below 70 degrees, well below the requirement of 100 degrees. And here is the dynamic zone development induced by thermal expansions. At the time of placement the fuel cells, there's minimal of failures in the models. Only a little of failures, shear failures, happen at the corner of the repositories. However, as the temperature increase because the volumetric strength induced by the thermal temperature change, and we're gonna have the failures around the repository at 100 years. And at 1,000 years, there are excessive failures here, as you can see. All of the rocks surrounding the repository were in damage with the very high tensile failure amounts here at the top and the bottom of repositories. And even the, in RSU, the model didn't converge. So it implies that the repository were not stable at 1,000 years time. It also implies that the spacings between the room are not enough, and we need to increase the spacing between the room to be more than 25 meters. The next application we discussed today is the effect of the seasonal temperature change on the slope stability. This is a very simple models, and it's basically a case study when we evaluate the effects of the temperatures and on the slope stability. And we have 4 scenarios. The first one is without the geosynthetic reinforcements. The second one is with geosynthetic reinforcement here. And the third one is we doing the SRF in the winter, and another one is in summer after that winter. And for all of the models running the thermal analysis, we always run a thermal cycle for several years in order to establish the initial condition. And here is the materials using in the simulation, and it's quite simple. There's nothing fancy, just a regular Moore column with no softening behaviors. The zero textile have the tensile strength of 400 kilonewton per meters, and the expansion coefficient of 1.7 E minus 4. The thermal properties were chosen at the typical value for the clay soil. And you can see here, we apply the climate area condition on the top of the models to account for the seasonal thermal changes. The constant heat flux will apply at the bottom of the model to account for the heat radiation from the Earth or transfer from the Earth core. Here are the SIF value from the analysis. Without the reinforcement, the SIF equal to 1.15. And the second one, when you install the reinforcement, it increased to 1.25 as expected. However, in the winter, the SIF is 1.14, and the summer after that winter, it goes to 1.15. It was quite surprised for us when we first see the value. We might think that, okay, there's something wrong with the model, there's something wrong with the input parameters. However, we look at the model closer, and it's quite interesting here. Here is the actual force. When you look at the actual force of the geotextiles before the safety factor calculation and without the temperature effect, we have the value of the actual force in tensile force in the geotextile 177 kilonewtons, right? However, here in the winter, because of the contraction of the geotextile, there are more tensile stress acting on the geotextile. It even exceeds the capacity of the textiles at that critical point right here, because they the critical surface right here, and it cut through the geotextile right here, and that on top of the contraction of the textile is snapped at right at that point. And then the slope behaves similarly to the one that has no reinforcement. And because the geotextile was snapped, it's no longer contribute to the stability of the slope in the summer as well. And you can see that the SIF value here is just exactly the same with the SIF value here, with, in the case that you have no geosynthetic. It's quite interesting. The last example I'm presenting today is the design a thermosiphon for eye-rich region. So many buildings in the north are built on a strong foundation of eye-rich permafrost. Because of the climate changes, the air and the ground are warmed up, as you all know, and thawing that permafrost. So the building in the north right now, they are increasingly being built with very expensive, yes, very expensive, but effective thermosiphon system. In this example, we are going to model a flat loop. Here's a flat loop, evaporators, thermosiphons, and similar to other models. Before installing the thermosiphon, the model will run with several years to establish the initial temperature distributions using the the climate variable condition at the top and the flux at the bottom. And after that, the thermosiphon were installed 1 year before the construction of the foundation right here. And then the historical point will add underneath of the foundation to monitor the temperature change over time. And the purpose of the thermosiphon here is try to keep the soil underneath of the foundations frozen at one time, or keep it permafrost. Here are the materials properties used in the models. For thermosiphon, we just used Zerling and Hein methods with speed and air temperatures from the climate variable conditions. And we also assign the temperature of 18 to the inside of the concrete foundations to represent the heated temperatures. And we also have the insulation go outside of the foundation here, and the conductivity of the insulation is 4E-6. And here is the contour of the temperature distribution here, and you can see that from the contour on of the point below the foundations was frozen for another 3 cases. And we can also look at the temperatures history of that point, and you can see that throughout 2 years, the temperatures was always maintained below the frozen point. And that concludes my presentation today. and I will try to answer as many questions as I can. And so let's start with these questions. So the first question I got is, let me summarize the question. So the question is to see if the change in the strength of the soil is incorporated in IH2. So that is really a good question because now we're talking about the uh, thermo-induced strength of soil. And right now, so we have many, actually there's three ways to do that currently. The first and the most simple way is we're going to have a function of the property by the temperatures. Like for example, you're going to have the tabular form of the cohesion changing with the temperatures. And as soon as the temperature change, you can just go to the table, interpolate from the temperature, and get the value that you want. So that is easy. But that need experiments and data and a lot of work to get that data. But it's simple. The second way to do that is similar to how we do the calculation for the unsaturated stress, where we don't account for the strength, but we account for the stress, similar to the way that we change the stress for the unsaturated soil. And the third way is we do add a state variable where we consider the temperatures, uh, unfrozen water content in the soil all together, as in the similar way to that we do with the unsaturated soil models. So to answer your question in short, we currently I actually don't have the capability to doesn't have the capability to do the state variable approach, but you can certainly input at a tabular form for strain and the temperature change. Okay, so another question I have here is there any major difference between the convection boundary conditions used in artificial ground freezing um, with the and the climate boundary conditions used to simulate ground surface in other simulations. So right now you're talking about the two boundary conditions in IH2. The first one is the convection boundary condition, and the second one is the climate boundary condition. So uh, the climate boundary condition actually include the convection boundary condition into the system, where it consider the effect of the air temperatures and wind speed to the equation, whereas the convection system is we consider everything at once and we come up with the heat transfer coefficient, like we call it like effective heat transfer coefficient to consider every of the effect at once. So both can be used interchangeable, but the important thing is we need to find the equivalent value to use for both. Does the program account for the air convection? Yes, the program does account for the air convection if you use the correct value for the convection boundary condition. You can get the equivalent heat transfer and do that for the convection boundary condition. Okay, thank you very much. And sorry that we running out of time now. And if there are any question that I haven't able to answer, yes, we will wrap up everything and we will contact you for the answer. Thank you very much, and looking forward to see you on our next talk.